All right, so this is section 16.2a, video number 2. We want to evaluate a line integral, because that's again what the integral with the c down the bottom means, of 2x ds, where c consists of the arc c1 of the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment c2 from 1, 1 to 1, 2. So if we kind of sketch this in our two-dimensional plane just to see what the projection looks like, we're talking about the part of the parabola y equals x squared from 0, 0 to 1, 1. So from 0, 0 to 1, 1. And we know it kind of looks like this, and it curves. Kind of missed my dot, so I'll make my dot bigger. There's 1, 1. And then we're talking about the line segment, which goes from 1, 1 to 1, 2. So basically it extends straight up 1 unit. So we've really got two different pieces that we have to perform our line integral over. So if we look at it in 3 dimensions, we're basically talking about, so let's see if I can keep the colors consistent here. The blue part down here from 0 to 1, and then the green part extending from 1, 1 to 1, 2. So the idea is whatever this curve looks like, 2x specifically, it's going to look something like this. If we extend this thing up, so I guess we can actually figure out what these values are. When x is 1, the z value, excuse me, is going to be 2. So right here where x is 1, these z values are both 2. So I guess I can extend that up a little bit taller just to make it look like it's more like 2. And it'll be linear because it's going to stay that way. And then it's going to go from there and curve its way down, something like that, something towards the origin. It really should kind of come out and more, it's not the best drawing ever, that's for sure, but that's kind of what it looks like. So the ribbon that we're looking at is basically going to be this piece right here, and then the piece that goes like that kind of winds its way around from the top of this down to the bottom. Not exactly the easiest thing to sketch. I'm not the best at it, but that's the general idea. So we have to break it into 2 separate pieces. We have to deal with C1, curve number 1, which was the parabola part. So that's y equals x squared. We're going to have to parameterize that. Okay, this is a perfect case for a trivial parameterization, in which case we're just going to say x is t, and if x is t, plugging t in for x, you get that y equals t squared. So there's your trivial parameterization. Whoa. Parameterization. Okay, and we know that that's going to go from 0 to 1. Because if I plug 0 and 1 in for both x and y, I get 0 to 1. So in this case, t is going to go from 0 to 1. Okay, not always the case, but in this case it will be. However, the next piece is linear. That's the part where basically the function is x equals 1. And because it's linear, now we have to think about this. How do we write the equation of a line in parametric? Well, x is always 1. Y starts at 1, and then it increases by 1 over this interval. So it's 1 plus t, going all the way back to when we first started writing parametric equations of lines. This is a linear piece, so it's linear. So we go with a linear parametric equation. Anytime we have a linear piece, the bounds are going to be 0 to 1. Because basically all you're saying is the beginning is going to be what we're going to call our time 0. The end of the linear piece is what we're going to call time 1. It's always going to be that way when you have to parameterize a line. Okay, so in order to do our line integral now, the line integral, let's go with orange, the line integral over c of 2x ds has to be split. We need to do the line integral over c1 of 2x ds plus the line integral over c2 of 2x ds. Okay, for c1, I know my bounds are 0 to 1. Okay, we came up with that for t. 2x, well, x was defined as t in our first c value, so that's going to be 2t. ds, remember, is the derivative of the x and y pieces squared, added together, and then take the square root. So dx dt is 1 squared. dy dt is 2t squared dt plus the integral over the c2 part. Again, it's a bounds from 0 to 1 because it's linear. It will always be that way. So if I were to plug in the x value, in this case, x is 1, so it's literally just going to be 2 because it's 2 times x, which is 2 times 1. Remember, we're looking at the green part now. It's going to be the derivative of x squared. The derivative of x here is 0. The derivative of y is 1 dt. So that second one's going to be really simple to deal with. It's just going to be all constants. In the first one, we're going to have the integral from 0 to 1 of 2t integral of 1 plus 4t squared dt. Looks like we'll have to do a bit of a u substitution. The second one will be really simple. It'll be the integral from 0 to 1 of 2 times the square root of 1, which is just 2 dt. So we can finish that second one very easily. In the first one, again, a u substitution here, 1 plus 4t squared. du is going to be 8t dt. Solving for dt, we get du over 8t. We can change the bounds. So let's see, plugging a 0 in is going to give us a bottom bound of 1. Plugging a 1 in is going to give us 1 plus 4, so that's 5. I'm now going to get 2t square root of u times my new dt, which is du over 8t. The t's are going to go away. The 2 over the 8 I can pull out to the front as a 1/4. Integral from 1 to 5, I'll rewrite the square root as u to the 1/2. And now I'm finally ready to take an antiderivative to solve this problem. So let's see, I'm going to bring this all the way down here because it'll be a simple one. That's going to be u to the 3/2 here times 2/3. Don't forget the extra 1/4 out in the front. Evaluated from 1 to 5. This one, the antiderivative is 2t from 0 to 1. Plugging in a 1, you get 2. Plugging in a 0, you get nothing. So we're going to add 2 to whatever our result is from this other one over here. So let's see, simplifying the coefficients, that's going to give us, what is it, 2 over 12 or 1/6. And then we're going to get 5 to the 3/2 power minus 1 to the 3/2 power, which is 1 plus 2. It's not a very pretty answer, but that is the evaluation of the line integral. And the reason that this was important was a couple things. Again, we had to split it into 2 separate pieces. While it was a continuous function, well, it's not actually a function, while it was a continuous curve that was in the 2-dimensional plane, it was comprised of 2 separate pieces. So we had to do 2 separate line integrals to figure out what, again, the area of whatever that thin ribbon would be that was created by the function 2x above that line. As you can see, some of these do not take, some of these are not short, so try and go through these a little bit quicker, but some of them just aren't, we're not able to do that. All right, so example 3, We're going to evaluate the line integral over xy cubed ds, where the curve is comprised of x equals 4 sine t, y equals 4 cosine t, and z equals 3t. So what you should notice there is that, first of all, it's already been parameterized for us, which is really nice. It's also got 3 different variables here. We've got x, y, and z all as functions of t. And they've given us the bounds 0 to pi halves. That makes this really nice. So this is already in 3 dimensions. Now, what does this look like? No idea. I have absolutely no idea visually what this looks like. But what are we really trying to find? Well, we are taking the integral of some kind of a function here, which is really going to act as our density function because it's in 3 dimensions here. And this piece is our arc length. So really what you're going to have is a density times the arc length of a really, really, really thin strip. So what we're really finding here basically would be like the mass of, for lack of a better term, we'll call it a wire. We're only finding the mass of the wire. And this wire has a variable density. So when we're dealing with 3 dimensions, again, I have no way to figure out how to, I wouldn't be able to give a sketch for this, can't visualize it. But what we are finding is the mass of a wire with variable density. So we're given a density function and an arc length in 3 dimensions. All right, as far as actually doing the problem, it extends pretty much the same way. You're still going to take an integral from t1 to t2. This time it's just going to be a function of 3 variables. So f will be a function of x of t, y of t, and z of t. And then arc length in 3 dimensions is just the exact same idea as it is in 2 dimensions, except we have the z component. So it's going to be the ds part is the square root of dx dt squared plus dy over dt squared plus dz over dt squared dt. All right, and again, the nice thing was here, they parameterized everything here for us. So that does make it a little bit easier as far as we don't have to go through that process. So we are going to take the integral from 0 to pi halves of our function parameterized. So x, y cubed, we have to fill in the stuff. So x was 4 sine t. Y cubed is going to be 4 cosine of t cubed. So that's going to be 64 cosine cubed of t. And then ds is all the derivatives squared and added together underneath that square root. So derivative of the x component is going to be 4 cosine of t squared. The derivative of the y component will be negative 4 sine t squared. And the derivative of the z component is just 3 squared dt. All right, so let's hope that this stuff simplifies a little bit. I have no idea. It's been a long time since I've done this one, so let's see what we get. I do know that when I square this, it's going to give me 16 cosine squared plus 16 sine squared. Well, that's just going to be 16, because if you factor the 16 out of that, you're going to get 16 times cosine squared plus sine squared. So that gives me 16. This part is going to give us 9. And 16 plus 9 is 25. Wonderful. The square root of that is going to be 5. Okay, I'm not going to write all of that out, but that's what that's going to be. So this part right here is 16. That part is 9. The square root of that is going to give you 5. Perfect. That's a constant. I can pull it out to the front. So really, I'm going to get, let's see, 5 times 4, which is 20, times 64. I don't know what that is. I'll figure that out in a second. integral 0 to pi halves of sine t cosine cubed t dt. All right, so let me go ahead and work this one out. So 20 times 64 is going to be, let's see, 10 times 64 is 640. If I double that, it's going to be 1280. So I'm pretty sure I get 1280 out of that, unless I made a silly mistake. This part, we're going to have to do a u substitution. U is going to have to equal cosine t, which makes du negative sine t dt. dt is then going to be du over negative sine t. We can change the bound. So we'll get 1280 integral. So cosine of 0 is 1. Cosine of pi halves is 0. When I do my substitutions, I'm going to get sine t times u cubed, times u cubed times dt, which is du over negative sine t. I like the fact that that extra negative is there because it's going to allow me to flip my bounds back over in a more correct form. So we're going to get, oh, geez, every time I touch the screen with my palm there, it moves there. So we get 1280 integral from 0 to 1 of u cubed du. So that's just going to be 1280 times 1/4 u to the 4th from 0 to 1. So 1280 over 4, believe it or not, that works out nicely. That's going to be 320. And then if I plug in 1 for u, I get 1. If I plug in 0, I get 0. So we should get 320. And that actually is the answer because I have it written down on my paper. So that is the mass of that wire over that specific curve. All right. I think I'm going to stop it there, and I think we should be able to come back and finish off the last 3 examples in the next video. I don't want this one to go long. The next example is a relatively long example, so we'll come back with a 3rd video.